So welcome back, children. In the previous video we discussed the cells, EMF and internal resistance. Actually, I planned to continue on that. I wanted to talk about cells connected in series and cells connected in parallel, and that is how it is given in your textbook too. But then I'm going to take a little detour and then come back and revisit it, because I feel that it is very important for you to know something else before you even touch cells in series and cells in parallel. Okay? And that something is Kirchhoff's laws. Okay? So we'll talk about Kirchhoff's laws now, or Kirchhoff's rules as they are given in your textbook. We'll talk about them first, and then we'll try to do some problems with Kirchhoff's laws, and after that we can come back and revisit your cells with their EMFs and then internal resistances, and see what happens when you connect them in series and also in parallel. So let me talk about Kirchhoff's laws now. Or rules. Kirchhoff gave us two laws or two rules. Okay, one is called as the current law, and the other one is called as the voltage law. Very simple to remember. Okay. One is a current law, and the second one is voltage law. Very easy to remember, right? Okay. This current law is also called as the junction law. And the voltage law is also called as the loop law. Now let's talk about the first law, which is the current law. Okay. Kirchhoff says that in a circuit, in an electric circuit, and if you take a junction, the amount of current that is entering the junction should be equal to the amount of current that is leaving the junction. Okay? It's a very simple law. You take a junction in a circuit, in an electrical circuit, the amount of current entering the junction must be equal to the amount of current leaving the junction. Okay? So let me just draw a circuit. Let's say you have a voltage here, a battery here. Now let's say you have a simple circuit like this. Okay. So you see, this is V. I can call this as R1. This could be R2. This could be R3. So which is a junction? I can call this as a junction. Okay. So you see there are 1, 2, 3. 3 wires meet here. That's a junction. And likewise, I can call this also as a junction, because 1, 2, 3 are more wires can meet at a position. So junction. Okay. So let us suppose that this battery sends current I. Okay. So that is the current entering this junction. Okay. And let's say there is a current I1 through this line which goes through this resistor. Let us suppose that the current I2 is going to go through this resistor. So what the current law says is that the amount of current entering the junction must be equal to the amount of current leaving the junction. So simply I is equal to I1 plus I2. Okay? So it is as simple as that. The amount of current entering the junction is equal to the amount of current leaving the junction. So what does it mean first? It means that no charge accumulates there in the junction. Now think about it. Suppose charge is flowing through the junction. Okay. And now, if the amount of charge entering the junction is not equal to the amount of charge leaving the junction, what will happen? Some charges will accumulate, right? So it will keep accumulating because there is current flowing. So after some time, you will have a lot of charge at the junction. So that doesn't happen. Okay. So this is more like, this law is more like the law of conservation of electric charges. Okay. So it's like a pipe a line. So let's say like you have a water pipe. Okay. Then the amount, if you take any junction, the amount of water entering the pipe must be equal to the amount of water leaving the pipe. If that is not happening, what will happen? Water will accumulate and pressure will build up, and then the pipe will burst. Okay. It's quite possible that the pipe bursts if there is enough pressure. Okay. So that doesn't happen here. So there is a smooth flow of current in a circuit. Then this is what must be happening. Amount of current entering the junction must be equal to the amount of current leaving the junction. That is the first law. That is the current law. Okay. Well, this law, if you see, it's not just about the junction. You take any point in a circuit. Okay. Even though he talks about the junction in a circuit, you take any point. For example, let me take this point. Even here, that is true. Why? Because the amount of current entering the junction must be equal to the amount of current leaving the junction. See, I is the current that is entering the junction, and then I is the current leaving the junction, or rather, leaving that point, I should say. This is a junction, this is a point. So you can say that at any point, in fact, like it's a much more refined version of this, at any point in a circuit, the amount of current entering that point must be equal to the amount of current leaving that point. Okay? So that is what it actually means. So this law is law of conservation of electric charge, in a different form. Okay. So it is such a simple law. So that's your current law. Then the second law. So that's the voltage law. So what does it say? So like I can say it's conservation of charges, right? So this talks about conservation of charges. The amount of charge, the charge that enters at junction or a point should be equal to the charge that leaves the junction or the point. So that is the conservation of charges principle. The second one is the voltage law. What does it say? It says that in a circuit, in a closed loop, the algebraic sum of all the potential differences in the closed loop must be equal to 0. Okay. Suppose, let me take this loop. So this is a closed loop. Okay. I start from here and then I come back to the same point. I can come back like this, or I can even come back like this to the same point. So in a closed loop, the algebraic sum, there will be plus voltages, will also be minus voltages, positive voltage drops and also negative voltage drops. Okay. So the algebraic sum of all the voltage drops in a closed loop must be equal to 0. Why? Again, that's obvious, right? So you see, I start from this point and then I come back to the same point. What would be the potential drop total? See, this point will have the same, right? I start from one potential, I come back to the same potential. So then what is the net potential difference? 0. Because this point will have some potential value, and when I come back, then I come back to the same potential value. Then what's the potential difference between the initial position and final position? 0, right? So that is exactly what this is about. The potential drop or the potential difference in a closed loop of a circuit the algebraic sum, I should say, the algebraic sum of all the potential differences in a closed loop of a circuit is 0. That is the second one. I will say the sum of all the potential drops. Okay. Say I is equal to 1 to n. All the components 1, 2, 3. If you take a closed loop, okay, must be equal to 0. That's the second law. So using these two laws, it's very easy for you to solve any circuit problem. Kirchhoff's laws would be used extensively in electrical engineering. And if you go study electrical engineering, then Kirchhoff's laws will form the basis on which everything else is built. Okay? So there are two simple laws. One is the current law, the other one is the voltage law. The current law is also called as a junction law. And it says a very simple thing. All it says is that in an electric circuit, at a junction, the amount of current entering the junction is equal to the amount of current leaving the junction. Think of a water pipe. So the amount of water entering will be equal to the amount of water leaving. Okay? So that is the first law, the first rule. And then the second is voltage law. That's also called as the loop law. And it says that the algebraic sum of all the potential differences in a closed loop of a circuit is 0. So the first law represents the conservation of charges, and the second law represents conservation of energy. Okay? So you start from here, then you come back to the same position, then potential differences 0, it's nothing. Okay, the initial potential and final potential is going to be the same. So it's law of conservation of energy in a different form. Okay. Let's see how we can use these two laws to solve circuit problems by taking up an example, and we'll proceed from there. Okay, using those two laws that we've just discussed, let's try to find out the current in the circuit. The current through this resistor, the current through this resistor, and the current through this resistor. Okay. This is a very simple circuit, so I will do it I will try to find the current in the circuit using Kirchhoff's laws. Okay. And then we can look at more and more complicated circuits a little later. But I will start with this simple circuit. Okay. So what I'm going to do, I'm just going to do a few things now. Okay, first, I'm going to assume that I is the current which is coming out of the battery. So this is I. That's a current coming out of the battery. The battery is going to supply this current. Okay. So clearly, whatever goes out of the battery should come back to the battery, right? So that's I. Okay. I is the current leaving the battery, and I is the current which is entering the battery. So that is given. Now you come here and then you find a junction here, right? You find a junction here. So now can I use the first law, the junction law? So what does it say? It says that the amount of current entering the junction must be equal to the amount of current leaving the junction, right? So I is the amount of current entering the junction. And I don't know what current is going to leave the junction, so I'll say it's I1, and I'll also say this is I2. Okay. See, the direction doesn't matter. You don't have to correctly guess the direction. Doesn't matter at all. If a direction is wrong, if you solve the equations that you would get a negative number for the current. If you get a negative number for the current, it means that the direction you have chosen is wrong. The value of the current is all right, but the direction you have chosen is wrong. So in that case, you have to come back and change the direction, that's all, finally. Suppose I do this, I get some number, and it says say I2 is minus say 2 ohm or 2 amps or something. If I get minus 2 amps as the value of I2, then immediately I will come back and then change the direction of I2 like this. And now I2 is 2 amp in this direction. So it does not, when you get a negative number, you don't have to change the magnitude. The magnitude of the current is the same, only the direction of the current will have to be changed. If you get a negative number, it means that you have got the direction wrong, not the magnitude, the amount of current wrong. Okay, that is correct, but only the direction is wrong. So you don't have to worry about it at all. You can randomly choose the directions. Right now, I'm going to go with this direction for I2 and this direction for I1. If I'm wrong, I'm going to get a negative number for either I1 or I2. Let's keep that in mind. Okay, so that is the junction. Okay, I apply the junction law here. So what does it say? My first equation is the current, amount of current entering this junction is equal to the amount of current leaving the junction. I can do the same thing for this junction also, but it doesn't matter now. So I is equal to I1 plus I2. So how many unknowns are there? I don't know what I is. I don't know what I1 is. I also don't know what I2 is. So there are 3 unknowns in this circuit. Okay. Clearly, when I talk about this junction, what will happen? I1 is coming here, I2 is coming here. So there are 2 currents entering this junction. There is only one current I leaving the junction. I will get the same equation again. So I'll just go with this equation. There are 3 unknowns. I don't know I don't know I1, and I also don't know I2. So I require 3 equations. That you know. There are 3 unknowns, and I require 3 equations. One of them is this equation. So this is equation 1. Okay. So the second thing that I need to do is assigning the potential drop directions for these resistors. Okay. So the way to do it is, say I have chosen the current. I am free to choose the current direction, right? I have chosen I to be in this direction, I1 to be in this direction, I2 to be in that direction. No problem. Okay, I have chosen the direction. That's totally up to me and arbitrary. I could have chosen any direction for these things, but I have chosen this direction, but it's perfectly okay for me to choose these directions. I am free to choose these directions. But once I have chosen the direction, the next step I have no control. Okay? I just need to follow this. If I take this resistor, the current entering the resistor will have positive potential. The current leaving this resistor will have negative potential. Okay? Because I have chosen I to be in this direction, I is entering the resistor here, so positive. Leaving the resistor there, it is negative. Okay? Now, I will come here. I1. I will talk about this resistor. So I1 is entering this resistor here. So it is positive. So leaving the resistor here, it is negative. Okay? And then I2 is entering this resistor here. And then leaving the resistor here, so it's negative. So once I've chosen the directions, I cannot arbitrarily choose this is negative, this is positive, this is positive, this is negative. I can't do that. But once I've chosen this, the direction of the current, then I have to choose, I have to go with this rule. Okay? The point at which the current enters the resistor is positive, and then the point at which the current leaves the resistor is negative. I have no choice. So this is positive, this is negative, because I have chosen this to be the current direction. And for me, this is positive and this is negative because I have chosen this to be the current direction. And this is positive and this is negative because I have chosen that to be the current direction. So that's where the current enters and this is where the current leaves. Right? Done. Okay. Now, let's see what happens here. Here, what do you have? what would be the potential drop across this? That would be IR, right? I mean current into the resistance. What's the current going through this? This is I. What is the resistor here? 2. So what is the potential drop here? 2I is the potential drop here across this resistor. And what about this? Well, I2 is the current flowing through it. 4 is the resistor. So 4I2 is the voltage drop across this resistor. And what about this then? So I1 is the current flowing through this. 3 ohms is the resistance. So 3I1 is the voltage drop across that resistor. Right? Okay. Now everything is in place. Now I can apply this second Kirchhoff's law. Okay. What is that? The loop law. In a closed loop, the algebraic sum of the potential differences is equal to 0. Okay. So how many loops are possible over here? I can choose this as loop 1. Let's say I can choose this as a loop. It's a different color. This is the loop. This is also, I can choose this as a loop, second loop, or I could have chosen this as another loop. Okay. There are 3 loops possible for me. But 2 loops are enough. Any 2 loops are enough. I can choose these 2, or I can choose these 2, or I have chosen these 2. Any 2 loops are enough. Why? Because I already have an equation here. There are 3 unknowns. I need 3 equations. I already have an equation from the current law. Then all I need are 2 more equations. So I can choose any of these loops. If I label them, let's say this is 1, this is 2, and this is 3. I can go with 1 and 2, or 1 and 3, or 2 and 3. Okay. And the third would be redundant. I wouldn't need it. Okay, I can use that too, but that would not be required, because you can solve for these 3 unknowns using 3 equations themselves. Why would you need one more equation to complicate things? So 2 are enough. Which 2 you are going to choose? That's totally up to you. Except that ensure that your loops cover all the branches. The set of loops cover all the branches. Say 1 and then 2. You see, I have not left any branch uncovered. Everything is covered. Or if you take this 3, and then when I take 3, this is not covered. Right? So I can either use 1, which covers this, or 2, which also covers this. So that's all. Okay. So 2 loops are enough. I'm going to go with 1 and 2. Thank you. Okay. So I'm going to go with 1 and 2. So let's say I'll start at some point here. Let's say I'll start from this point. I will do this and then I'll come back to this position, same position. Okay? Okay. What is it? Okay, I'm going to go this way, right? I'm going to do this clockwise thing. When I do the clockwise thing, look at this point. I'm entering this resistor at a positive voltage, potential, right? As I traverse, how do I enter? I enter it at the positive potential. So I say it's positive. So positive voltage. So I say this is 2I. That's for this. And then I come here. This I'm coming here. Again, this resistor, how am I entering? I am entering at the positive potential again. So again positive. So that's going to be plus, what's the potential? 3I1. Okay? And now I come back here. I have the battery. How do I enter? I enter through the negative potential. So I will say it is minus 10. And I will come back to the same position. So the sum of all this must be equal to 0. Okay? I am traveling like this. You see, these positive and negative symbols are already decided. They are based on the current flow. They are based on the current direction. I had chosen one current direction, and for that current direction, this was positive, this was negative. That's all. Now I am traversing. I am traversing in the clockwise direction. We traverse in the clockwise direction. Notice here, this is going to be positive. So I am entering this at the positive point. So plus 2i. So now here again plus 3i1, because I am entering here at the positive. Then when I come here, I enter this battery at the negative terminal. So I say minus 10, which is equal to 0. Now this will give me one equation. 2i plus 3i1 equal to 10. Okay. Let's see. Should I traverse this loop only in the clockwise direction? No, it's not needed. Okay, what I'm going to tell you now is a little bit extra, but pay attention here. It's totally up to you. You can either traverse it this way or you can traverse it in the anti-clockwise direction also. It's not going to change the equation. That's what I'm going to show to you now. Okay, you see, let's say let me start from the same point. This time instead of going this way, let me go this way, like that. Okay, like that. Let's see what happens here. Okay, I'm going to draw that in blue. Okay, I'm coming this way, right, in the anti-clockwise direction to the same point. I'll start from this point. Now I'll go in the anti-clockwise direction and go back to the same point. So how do I enter here? As I do it, I'm entering the battery at the positive terminal. So I'll say this is 10, plus 10, because I'm entering here is plus 10. Notice I put minus 10 here when I did it like that. But when I come like this, then it is plus 10. Okay, and I come here. What happens? I enter this resistor through the negative point, negative potential. So then it will become minus 3i1. And then I come here. Again, I enter this resistor through the negative point. So then again minus 2i. And then I come back to the same position, point here. Okay. That is again equal to 0. You see, if you take it there, then also 10 is equal to 3i1 plus 2i. Notice here, you get the same equation whichever direction you go. So the direction of your traversing this circuit does not matter. You can start from here, you can do a clockwise loop, or you can start from the point and then you come back to the same point to an anti-clockwise loop. Doesn't matter. Either way, you are going to end up with the same equation. So the direction of you traversing this does not matter at all. Okay, that's you need to understand that. Okay. So I'm going to ignore this. I'll come back to the same right. So I'll ignore this. This is just for demonstration purposes. So I got this equation. So this is equation 2. 3 unknowns. I got 2 equations. Now I'm going to take the second loop here. Let's see like what kind of equation it's going to give me. Where should I start? I can probably start from this point. I can start from any point, doesn't matter. I should come back to the same point, that's all. Okay. Again I'll do clockwise here. So I go here, and how do I enter? I enter through this resistor at the positive point. So it's going to be positive thing. So 4i2. 4i2 is this potential drop, positive for me. And I come back and I enter here. What happens? Well, I enter through this resistor through the negative potential. So I say this is minus 3i1. And then I come back and come back to the same point. So I complete the loop. So that must be equal to 0. So this is my third equation. And if I do it the other way, I'll get the same thing again. You see, this will be positive then and that will become negative and come back to be 0. So again I'll end up with the same equation. So this is 3. So this is equation 1, this is equation 2, and this is equation 3. There are 3 equations for it. Now I should solve them. Okay, so look at this. This is 2i plus 3i1. This is 4i2 minus 3i1 is equal to 0. I can do something. I know I is equal to i1 plus i2. So I can make use of that equation here, right? So then that will give me 2 into i1 plus i2 plus 3i1 is equal to 10. So that gives you 2i1 plus 3i1. So 5i1 plus 2i2 is equal to 10. So that's equation 4. Okay. And then I can take this equation 4i2, or I can say minus 3i1. I'll gather them. Minus 3i1 plus 4i2 equals 0. So equation 3. So can I solve? Yeah, I can very easily solve this, right? So I2 is 2 and 4, so I can multiply the top one by 2. Then I'll get 10i1. So 10i1 plus 4i2 is equal to 20. So that will be 2 into 5, right? The whole thing. Then minus 3i1 plus 4i2 is equal to 0. Now I need to subtract. I'll call this as 5 and this is 3 again, right? I need to subtract this equation from the first equation. Then 4i2 will go, and then I'll have only i1. Okay. So 10 minus of minus 3, I'm going to get 13i1. 4i2 minus 4i2 will cancel. So 20 minus 0, I'm going to have 20. So my i1 is going to be equal to 20 by 13. Okay, that's it. I got i1, and then I can find i2, right? I can make use of any of the equations to find i2, or I can solve i2. I could have so I multiplied this by 3 and then this by 10 and then added those two equations. But the point is that you should be able to solve for i2 using any of the equations. I want to use this equation. It's a very simple equation, right? 4i2 is equal to minus 3i1. So I'll do that now. So 4i2 is equal to minus 3. From here, I'll get 4i2 is equal to 3i1. But I got i1 here. So what is my i2? i2 is equal to 3 by 4 i1. But what is i1? i1 is 20 by 13 into 3 by 4. So this will be 5. So 15 by 13. So i2 is going to be equal to 15 by 13 amperes. You see, both of them are positive numbers, which means my assumed direction for the current is correct. Okay, so I1 20 by 13, I2 is 15 by 13. And what would be I? It's the sum of these two, right? So what is I? I is simply I1 plus I2, so that is equal to 20 by 13 plus 15 by 13, and that gives me 35 by 13. So that is my I. So I know that 35 by 13 ampere is flowing through this, and then here it's going to become 15 by 13 amperes, and here it's going to become 20 by 13 amperes. 20 by 13 amperes. Okay. Now I know the current in all the branches of the circuit. So it's a very simple problem, and we have solved for the current using Kirchhoff's laws. So what did we do? I reiterate again. So we said, okay, first we had the circuit, and then I chose a junction, and at the junction I said the incoming current is equal to the outgoing current. So I is equal to I1 plus I2. I chose directions. It's totally up to you. I did not know that I2 will be flowing that way or I1 will be flowing this way. I did not know it. But I chose a random direction. I chose this to be this direction of current. Okay. So then I got these numbers. If I had chosen one of the directions wrongly, then I would have had the same thing except that one of them would be a negative number. Okay. And if I get a negative number, so for example, if I2 is minus 15 by 13, then I should change the direction of I2. So I2 is not in the same direction as I had assumed. Okay. So that's it. So like first I looked at the circuit, and then I chose the current direction. That is number one. First one is choose the current direction. Steps. Choose the current direction. Okay, it's arbitrary. You can choose whatever direction you want. Okay, there's no bearing on the result. Okay. If you're wrong in assuming the direction, then you get a negative number. That's all. Second, once you have chosen the direction, then assign the voltage drops. That is, assign, what does it mean? Assign positive and negative symbols. Okay, here. The current is chosen to be in this direction, so current is entering here, so it's positive. Leaving there, so it's negative. So assign the voltage drop directions. Okay, you do that. Once you have done that, then 3, identify the loops. Okay. If there are n unknowns, then n minus 1 loops are enough. Okay. If there are n unknowns, okay, then you require n equations. N equations are required, and you see how many current equations you have, and then now you have only one. In some cases you may have more than one current equations. In that case, the number of loops you would require would be adjusted. But in here I got only one current equation. I have 3 unknowns, so I require 2 more equations. So I need to identify 2 loops. So identify the loops. Okay. What is the condition to identify the loops? Ensure that all the branches are covered. Okay. Then 4. Form the equations, solve them. Equations, solve them. Okay. 5. If any value is negative, change the current direction. You are done. Change the current direction. See, these are the steps. Choose the current directions arbitrarily. This is arbitrary. Okay? You can choose directions as per your whims and fancies. 1. Second, assign the voltage drops. Once you have chosen the direction, you have no choice on how the voltage will drop. The current flows in this direction, this will be positive, that will be negative. The current flows in that direction, and that will be positive, this will be negative. You have no choice about it. Do that. And then 3, identify the loops. The number of loops, you identify those loops. And then ensure that all the branches are covered in your set of loops. Okay. Then 4, then form the equations. You use the loop law to form the equations. Second one. Okay. And then 5th is Okay, once I solve them, then see if any value is negative. If any value is negative, then go to the branch, change the direction of the current. You are done. So this is how you apply Kirchhoff's law. I'm going to solve the same problem, but I want to take a different direction now. I've chosen this direction, these directions. They happen to be the right direction, so I got positive numbers. I'll change one of the directions now, and then see how the value changes. Okay? See. Okay, we are going to solve the same problem in a slightly different way. Okay? By using Kirchhoff's laws. Just to demonstrate that the direction of the current doesn't really matter. We are going to get the same answer. Okay, first I'll just take this as I. Which direction? Let me just choose this direction as I. It makes logical sense to me. So current leaves the battery, so it goes that way. But now let's say that this is my I1 and this is my I2. You see, in the previous case, the previous way of solving this problem, I had assumed the current to be in that direction. Now I am assuming the current to be in this direction. Okay, let's see what's going to happen now. Okay, same. So I'll take this junction. I'll use Kirchhoff's current law. What would that give me? I is equal. Okay, here let's see. What's incoming current? I is incoming, and I2 is also coming in. So the incoming current is I plus I2 here, right? And that must be equal to what is outgoing I1. So I1 is the only current which is going out, and then I and I2 are the currents which are coming in. So what does the law say? The amount of current coming in must be equal to the amount of current going out. You see that this appears to be slightly different from the equation we had first. It doesn't matter. You're okay with this. So this is I2 is I is coming in, I2 is also coming in, and I1 is leaving. So I plus I2 must be equal to I1. Done. I'll see the equation now. So what is the second step? Once you have chosen the current direction, now you need to assign the voltages, right? So here the current is in this direction. So in this resistor, it's going to enter here. So this is positive and this is negative. So then I will say this is going to be 2I. That's the voltage drop across this. Then the current is entering here. So this is positive and this is negative. So this is 3I1. And then current is coming like that. So then current must be entering here and leaving there, right? So leaving there, so minus, and this must be plus. So that would be 4I2. That's the voltage there. Okay. So now again, I have choices, right? I can have, there are 3 possible loops, and out of which I have to choose only 2. So I'll choose the same 2 loops that we used previously. I'll choose this loop and also this loop, and let me traverse the loop in the clockwise direction. So it doesn't matter. I can traverse this in the clockwise direction, I can traverse in the anti-clockwise direction or clockwise direction, or I can traverse this in the anti-clockwise direction. It doesn't matter at all. I can traverse these loops in any order, any direction I want. It doesn't matter at all. But for our purposes, I'm going to traverse this loop in the clockwise direction. Again, I'll start from this point and come back to the same point. So how am I entering this resistor? As I traverse like this, I'm entering it at the positive point. So it's going to be 2I. Okay, I come here. Then again, this is positive. So that is 3I1. Then I come back, I enter the battery and the negative terminal. So that's minus 10. That's equal to 0. So I say 2I plus 3I1 is equal to 10. So that's my equation 2. And then I'll come back to this one. Okay. So that would be, I'll start from this point and come back to it, right? So I do it here. How do I enter this resistance? I enter it through the negative point, right? So that's going to be minus 4i2. And then I come back. Then what do I do here? Again, I enter it through the negative one. So do minus 3i1. That is equal to 0. Okay? I can take minus is common, so I can take it there to the other side. So I will say like 4i2 plus 3i1 is equal to 0. That's my equation. I can take this as 3 and I can make it as 4, doesn't matter. So this is what I got. 4i2 plus 3i1 is equal to 0. Or I could have kept it like this itself. It's totally up to me. Doesn't matter. I have not changed anything here. Remain the same. So this is my equation 1, this is my equation 2, this is my equation 3. Now I need to solve. So what I got here? I got 2i plus 3i1. Okay? So 2, what is I? I can say I as I1 minus I2 right here. It's going to be I1 minus I2. Okay? Plus 3i1 equals 10. So what does it give me? 2i1 plus 3i1, that will become 5i1. But now minus 2i2 equals 10. That's my equation 4 from here. And what about this? Then I will say 4i2, I will say 3i1 and plus 4i2 equals 0. That's my 3. Okay? So how do I solve these two? Well, I can multiply this by 2, then I get 10i1 minus 4i2 equals 20. That's my equation 5. Then I get 3i1 plus 4i2 equal to 0. That's my equation 3 as usual. Okay? So now I don't have to, now I can just add them, right? If I add these two, then this will be common. So that will become 13i1 equals 20 plus 0 is 20. So what's my i1? My i1 is 20 by 13. Yeah, as it happened in the previous case. My i1, I get 20 by 13. No issues. But what about my i2? My i2 is slightly different now. Let me take this equation. 4i2 plus 3i1 is equal to 0, meaning 4i2 is equal to minus 3i1. So i2 is equal to now minus 3 by 4i1. So that is going to be equal to what? It would be minus 3 by 4 into 20 by 13. So 5. So minus 15 by 13. Well. The last time I2 was simply plus 15 by 13. This time I am getting minus 15 by 13. Meaning that the I2 direction I have chosen is wrong. So I just simply have to change the direction. And I2 will have the same value. What is that? 15 by 13. See, I get the right direction. That's it. Now what about my I? What does it say? What is my I? What is my I1? I1 is 20 by 13. My I2 is minus 15 by 13. So my I is I1 minus I2. So what is I1? It's 20 by 13 minus, what is I2? Minus 15 by 13, right? So minus 15 by 13. So it's going to be plus. So I'm going to have 35 by 13. You see, for I get a positive number. So this direction, my assumed direction is correct. So I'm okay with it. So that is 35 by 13 amperes, as usual, as it was in the previous case. Then I1 20 by 13. So that is this is a positive number, so I don't have to change direction. 20 by 30. But I2 is minus 15 by 30, so for that only I had to change the direction. So if you get a negative number, just change the assumed direction and everything else will fall in place. So that's it. Now you know, even though I started with this direction, after solving the equations, I know that I2 is actually flowing in that direction, not in this direction. Okay, so everything else now falls in place. So whether I do it the previous way or I do it this way, I will have the same results. Okay. The only thing that we need to remember is if I get a negative number, I just have to go and change the direction of that current. That's it. Everything else will be okay. So once you solve for this circuit, now you see this solution, I being 35 by 13 and I1 being 20 by 13 in this direction and I2 being 15 by 13 in that direction will remain the same whichever way you solve this problem. Okay. So both methods will lead to the same result. Hope this is clear to you.